Hello again. I hope that you have been able to get and digest some of what was in the last few videos. I know it's a little bit challenging to get used to the terminology and the truth tables and all of these propositions and conjunctions and all the rest, but keep at it. It will get a little bit better once you get the hang of things. So let's look at propositional equivalences in section 1.3. And also we're going to look at section 1.4 and quantifiers. So in section 1.3, uh, let's look first at an idea of what is a tautology and what is a contradiction. Now, a compound proposition that is always true is a tautology. So in every row of the truth table, if it always comes out to true for that proposition, then it's a tautology. A proposition that is always false, if every row ends up with false, then it's a contradiction. So look at table 6. If you have the proposition right here that P or not P. So I've made a column for P and a column for not P, and the proposition P or not P, well, you have to have at least one of those true. And so in the first row, we have one of them true, so that's true. In the second row, we also have one of them true. So that, because every row has true for the proposition column, then it's a tautology. And that should make sense because either a proposition P is true or the opposite of it is true. So either P or not P. Well, that's always going to be true. I'm either going to go to the store or I'm not going to go to the store. It's either going to rain today or it's not going to rain today. Of course, that's a tautology. The last column has the statement P and not P. So both have to be true in that case. Now, how can both P be true and not true at the same time? It can't be. And that's why in the rows or in the column, the last column, P and not P, we don't have any time when both P and not P are both true. So this is false always. So that's called a contradiction. Okay? It's like saying it rained and it didn't rain. You can't have that. All right? I'm going to move on. Oops. Back up a line. Okay. So logically equivalent propositions, see, that was talking about a single proposition. But when we talk about two propositions, they can be what's called logically equivalent. Okay. So logically equivalent is when the biconditional proposition 1, double arrow, proposition 2 is a tautology. Okay. Which means either they're, both of them being true makes it true, or both of them false makes it true, because that's what a biconditional does. If it's false, false, then that would be true. The biconditional would be true. Or if it's true, true, it would be false. The only time a biconditional is false is when one is true but the other's not. Now, if you have two propositions where the biconditional is always true, that's called logically equivalent. In other words, proposition 1 is logically equivalent with proposition 2. All right, and so so we use this 3-line equal sign. It means equivalent. Proposition 1 is logically equivalent with proposition 2. All right. Now let me move my video and then look at this truth table. All right. So what we have is we're we're doing the proposition not P or Q, and we're doing the proposition if P then Q. So because I have a not P in there, I made a column for not P. And of course, because I've got two propositions, P and Q, I need 4 rows. 2 squared is 4. So I've got my 4 rows, and not P or Q, well, if I look at the second and the third columns, if either one of them is true, then it's true. So you have true for the first row, but it's false for the second, because right here you don't have either one of them true. Then the third row is true, and the last row is true. So true, false, true, true. Now, in the case of if P then Q, well, when is a if-then statement false? It's false when it's true for the first part, but false for the second part. And if you look at the second and the third columns, I'm sorry, we're looking at the first and the second columns, because it's just P, not P. It's just P. So the second row has true for the P and false for the Q. So that's false. But all the other times you don't have true for the first and false for the second. In the case of false, true, false, false, that's going to be true. As we've talked about, watch the previous video if you're not sure about P implies Q. Anyway, after you get the truth tables done for those two propositions, you look at them and you see that every row is identical. So in that case, if one is true, the other's true. If one is false, the other's false. So we call this logically equivalent, that these two statements are logically equivalent. So that means that if you have something in the form of not P or Q, it's equivalent with if P then Q, or vice versa. If you know if P then Q, then you know not P or Q. All right. Next slide. Here's some other logically equivalents. You can look on page 27 of Rosen's text, but you can show that these other statements on page 27 are also tautology. So here's an example in this table right here. We've kind of already talked about these. P or not P, that's always going to be true, because one of them has to be true. P not or and not P is going to be false, because that's a contradiction in every row. And so these are equivalent. Now, and the last one is the one we just talked about, but there's more on table 4, page 17 of the text. Those laws, distributive law and other laws, are all tautologies as well, and therefore logically equivalent statements. So I'm going to quickly look at page 27 of Rosen's text. See if I can't bring this into the screen here. Okay, here we go. So this table 5 is a demonstration that these two very long statements are logically equivalent. But I wanted to look at table 6, and you can see some of table 6 here. All right, so we've already talked about some of these, but you can probably understand why a lot of these are correct. P or P, well, yeah, at least one of them, I mean, that's equivalent with P. If P is true, then one of them is going to be true. P and P is also going to be true if P is true. Now, P is false, P and P is going to be false. But a lot of these should make sense to you. commutative laws says you, in some cases, you can switch the order of things. As you see here, P or Q is the same as Q or P. So if you ever need to switch the order of the statements in a compound proposition, you can, if it's or if it's and. Associative laws, you can look at those. They get more and more complicated. Distributive laws, this is just like in algebra when you have something times a parentheses. And the operation inside the parentheses it has to be different from the operation outside the parentheses. But really, in algebra, it only works when it's multiplication outside the parentheses and then times addition or subtraction inside the parentheses. But here it works in both cases. De Morgan's laws we've already talked about. This is a way to negate an and or negate an or. And then absorption laws, they're just kind of a combination of some other things. We could prove these absorption laws are true based on the previous things. And then we've already mentioned the negation laws earlier. So just thought I'd mention that. Those are some examples. There's also more examples on further pages in Rosen's text. Here's some logical equivalences involving if-then statements. All these involve if-then statements. And then there's in table 8 involving biconditionals, the double arrow biconditionals. And then, so I think that's all. Now, example 5 shows an application when we're talking about English sentences. So you take your English sentence, you convert it into logical symbolism, and then you can apply De Morgan's law in the example here to it to get another statement. And so you can read that example. All right. Moving on. This talks more about De Morgan's law. The opposite of P or Q is not P and not Q. So if I said it's not true that I'll either go to the store or go to my office, the only way that for that to be not true is if I did not do both of them. In other words, I did not go to the store and did not go to my office. Okay? So that's the first law illustrated. The second law says it's not true that P and Q are both true. So if I said I'm going to go to the store and to my office, if you say no, that's false, then it had to be either that I did not go to the store or I did not go to my office. Okay? So you can see why De Morgan's law holds true. All right? It's just common logic that we use every day, but it's written in symbols. Okay? This is not, terribly complicated, really. All right, then the negation of or is the and of the negations. Or that's how to write De Morgan's law in words. Or the negation of and is the or of the negations. So anyway, moving on. So let's show, as in the example we just looked at in Rosen's text, let's show how we can apply De Morgan's laws or some of these other laws. All right, so show that not P and not Q is equivalent with if P then Q. All right, so you see that you have the negation of an and situation. All right, so you can apply the second of De Morgan's laws. And so the opposite of P and not Q would be not P or the opposite of not Q. Okay. Now, why did I have a double negative there? Well, in the original statement, I have a not Q, but now I've got to negate that. Remember, it's the negation of an and is the or of the negation. So I need to negate both of the original statements. Well, this original statement is not Q. So the opposite of not Q is what I'm going to have, which of course in the second line becomes regular Q. The opposite of Q is just Q. But then to convert that to an if-then statement, there's a few slides before we had shown that that's equivalent with P or Q. I could have just omitted this third line because let me go back a few. Okay, right here, it shows it here. In the third row of this table, not P or Q is equivalent with if P then Q. So we actually, in this example, have not P or Q in the second line of it. And then that could go right to P or Q. I actually don't need this statement in the middle here, or in the third line. But you could, as it explains here, you could do that using the third equivalence of table 7. All right, so you can also shown this using a truth table. So let's fill in this truth table and see what we get. So let me switch to using the marker. So first, we have two propositions, P and Q, and we're going to try to show that the left side of this equivalence is equivalent to the right side. So in other words, these are the columns I need. So I need to have the negation of Q. You see the negation of Q right here. So I'm going to have false, true, false, true. I'm just negating the Q column. Now I've got to do the and of P and not Q. So I'm going to look at the first column and the third column and do the and. Well, you have to have both of them true, and that only occurs in the second line where you have both the first column and the second or the third column true. So all the other rows are false. So that's that column. Now, what does this say to do? Well, this says not of that whole parentheses. Now, the parentheses is what we just did. And so the negation of that, well, I'm just going to negate everything. So every row I negate. So there we have it. All right. Now we have to do the last column, which is an implication. So it implies if P then Q. Now, when is an if then statement false? It's false when it's true for the first case, but false for the second case, which is occurring in the second line. That's when it's false. But as we said in the past, every other time it's true. Okay, if you recall, I said if I tell my granddaughter, if you clean up your toys, I'll take you to the park. The only time I'd be lying is if it was true that she cleaned up her toys, but I did not take her to the park. So that would be when I was telling a falsehood. But if she cleaned up her toys and I took her to the park, that would be true. I didn't lie. If she didn't clean up her toys, but I took her to the park, she did not clean. It's false that she cleaned up her toys, but I did take her to the park. That would still be fine. I didn't lie. I just had some other reason. Maybe she was nice in doing something, so I wanted to reward her. All right. Anyway, then if she did not clean up her room and I did not take her to the park, that would also be a true statement that I made. Okay. All right. All right. So let's move on. So I'm going to go on to the next slide. So the last item in this section talks about when is a compound statement satisfiable. Satisfiable means that you can find some situation where all the statements are true. And that's really the same as what we talked about where the system specifications are consistent. Okay, if I can find a situation, in this case a row of the truth table, where all the statements are all three of the, or that statement is true, can be true, then it's satisfiable. So basically I need to find a row of this thing where it ends up to be true in the last column. So in this compound statement, I have not P, I've got not Q, I've got not R. So I'll go ahead and do not P, not Q, not R. So I fill those in. And then I have to do this one here, which is P or Q. Okay? Or excuse me, P or not Q. So I'm going to look at the first column and the column here which says not Q. So I'm looking at the first column, P, and the not Q. So this is OR, so the first one's going to be true. The second one coming down is going to be true. The third one is going to be true. The fourth one is going to be true. Next one we have false, because I don't have at least one of these two things being true. Next one also false. Next one is true because I have at least one true, and the next one is true. Okay? Now the next column, Q or not R. So this time I'm going to look at the not R and the Q. Okay? Not R and the Q, and I'm going to ignore this. So not Q and not R. Excuse me, or Q or not R. So this one is true because I've got Q true. That's true. I've got Q true. All four of the first ones. I'm sorry. I do not have Q true here. And so I have an F here and an F here. So this one's going to be false. Okay. And then the next one, well, I have at least one of them true, so that's true. All right, so that one was okay. Okay. And then the next one, well, I have the Q true, so that's true. And then I have both of them true, so that's true. And then the next one, I do not have either one of them true, so that's a false. But in the last row, I've got this not R true. Okay. Now we're going to look at R and not P. So forget this. We're going to look at R and not P. So these columns are right next to each other here. R and not P. So that one is true. And that one is false because we don't have, in these two things, we don't have at least one is true. This one, we have at least one is true. This one, we don't have at least one true. TT, well, we have at least one true. We have at least one true here. We have at least one true here. And we have at least one true here, looking at the third and the fourth columns. Okay. Now the last column, you see that we have and for everything. So when is this triple and statement going to be true? Well, it's true when all three of them are true. Okay? And so all three of them are true, well, in the first row, but not in several in the last row. So all the other ones are false all the way down. I'm not going to copy that, but it's false all the way down here. But the first row and the last row are true. So what does that mean? Well, that means that this compound statement is satisfiable. Okay? Now, if we had gotten falses for everything, then we would say it's unsatisfiable. Okay? You cannot find a situation when all these propositions are satisfied, or the whole proposition is satisfied. Okay? All right, so then let's go to the next slide. Now, section 1.4 is on predicates and quantifiers. A predicate is the verb in the sentence. So like for all men are mortal. If I have a statement, all men are mortal. Okay, so the verb or the noun is men, all of them, all men, and the predicate or the verb is are mortal. Okay, but we want to be able to take statements that use predicates and quantifiers and put them into logical symbolism. Okay, so when we use terms like every or some or at least one or none, we're quantifying something. Okay, sections 1.1 to 1.3 do not really talk about how many things are the predicate is being applied to. So, like for example, the statement, all humans are sentient. To conclude this statement that a particular human is sentient, we don't have any logical mechanism, or we haven't talked about any way to go from all to a particular object or person. So we want to be able to express some property. The property is like the predicate. So all humans are sentient. So all humans is the noun, and the property or the predicate is that they are sentient. All right. Now, suppose we want to say that no computer on a network uses Unix. Then we can let P of X be the property that a computer uses Unix. So that's like your predicate. Okay. And let the domain of the propositional function, see, P of X is like a propositional function, the domain of the function be the set of computers, which are like the X's, on the network. So all the computers on the network is our domain, and we're saying that there does not exist any computer on the network that uses Unix, which is the P of X property. Okay, so our statement, no computer on the network uses Unix, becomes there does not exist an X in the domain such that P of X is true, or for all X, P of X is not true. Okay, so we're going to try to take statements and put them into precise logical terminology or symbolism. All right. Here's some examples. If P of X denotes the statement X is less than 7, what are the truth values for P of 5 and P of 9? So this is just basically saying that I'm going to apply the property that X is less than 7 to a particular value for X, in this case 5 and 9, and see what happens in terms of whether that's true or not. So P of 5 means that we apply the X is less than 7 statement when X is 5. So P of 5, the statement that 5 is less than 7, has the truth value of true. Of course, 5 is less than 7. But P of 9, which means 9 is less than 7, that would be false. So P of 9 is a false statement, while P of 5 is a true statement. Okay? So you see how we're taking a particular value and sort of applying the proposition or the predicate. Okay, look at the next example. If Q of xy denotes x plus y equals 8, what are the truth values of Q of 3, 6 and Q of -2, 10? Okay, now Q of 3, 6. Now remember, see the format of Q of x, y. So Q of 3, 6, we're going to plug in 3 for x and 6 for y. So 3 plus 6 equals 8. So of course that's false. So that statement, Q of 3, 6, is a false proposition. But Q of -2, 10, that would mean I'm going to plug -2 in for x and 10 in for y. So -2 plus 10, of course, that is equal to 8. So that statement, Q -2, 10, is true. All right. Now here's some other examples. Page 39 of the Rosen text uses the function a of c(n) to mean that a computer C, so the computer is the C, and N is the network. So this would be a situation if you have multiple networks in a maybe a university or multiple networks in a business. You don't just have one network, okay? So N is the number of the network or the name of the network, and C is the name of the computer, okay? So for example, the proposition A of Bauer, comma, Mercer Fack would mean that the computer labeled Bauer is connected to the network named Mercer Fack. Now obviously this example that I just put in there is not in your Rosen text. I'm not I don't have my name in the Rosen text, but there are other examples in there. But you get the idea how we're taking a function and we have two independent variables coming into that function. In this case, the name of a computer and the name of a network. And when would that propositional function be true? Well, if it's true that, that computer is in that network, and it would be false if that computer is not in that network. Okay? In example 6 on page 39, it refers to the programming statement if x is greater than 0. So you might have an if-then statement in a programming language. Now this is just in pseudocode, but whatever language it is, it would have if-then statements. You probably wouldn't have the comma here. But if x is greater than 0, then x becomes equal to x plus 1. So that statement, or that symbol, colon equals, in pseudocode or in some languages, means x becomes equal to x plus 1. So if P of x is that statement, if x is greater than 0, then x becomes x plus 1. So P of x is this. Then what would P of 3 be? Well, first it checks the condition. Is 3 greater than 0? So yes. So then x will become equal to x plus 1. So when it does that, then x would end up to be 4 in that case. Okay? So if it does that P of 3 statement, you would have that increasing and change the value of it. All right? So moving on to the next slide. Quantifiers. The universal quantification, basically universal means everywhere, so for all values in the domain. So if I want to make a statement that P of x is true for all values of x in the domain, then I can use this symbolism right here in red here. For all x, P of x is true. Okay? So that's a really brief symbolism for stating for all items in the domain that proposition is true. Okay? Now sometimes in the word problem situation, they might use the phrases for each, or for any, or for every. Well, for each one, that would mean like for each one in the domain. So that means for all of them in the domain. For any in the domain. In other words, you pick any in the domain, then that proposition is true. Well, that means all of them. Same thing for the word for every. Okay? So it's not just for all. You know, sometimes other phrases also have the same meaning as for all. Then an existential quantification of P of x is there is an x in the domain such that P of x is true. Now this is not saying how many there are, except somewhere greater than or equal to 1. There's at least one of them, okay? So there is an x in the domain such that P of x is true. So we're going to use this backwards E. So there exists an x such that P of x is true. There exists an x in the domain such that P of x is true. Okay? So how can we or think about when they're true and when they're false? Okay, for the first case, the universal quantification, for all x, P of x is true. It has the same meaning. Well, for any value of x in the domain, P of x is true. When is that statement false? If I want to say, if I'm saying that for all x in the domain, P of x is true, then to prove me wrong, how would you prove me wrong? You would find a single x, at least a single x, where it's false. And so the statement, the universal statement, is proven false when there is an x for which P of x is false. So all you have to do to prove a universal statement is find one counterexample. We call it a counterexample. All right. Now, if someone says all dogs are hairy, well, you know, if you can find any dog that has no hair, I think there is like one breed of dogs that has no hair, at least it doesn't look like they do, then you've proven that statement false. Okay. In the second row of this table, there exists an x such that P of x is true. How do you prove that false? Let's scoot over to the false. Well, you have to prove it false for that P of x is false for every x. Okay, so for all x, P of x is false. Or in other words, for all x, not P of x. Okay. More examples. To disprove for all x, P of x is true, in the green here, just show that there exists an x such that P of x is not true. So that's kind of what we were just talking about in the table. To disprove that there exists an x such that P of x is true, you got to show that for all x, not P of x. In other words, P of x is not true. Okay? So here's an example. Let R of x be the example, or the statement. 2x plus 3 is greater than x plus 7. Find the truth value of, for all x, R of x. All right, so how do we determine whether a statement for all x, R of x, is true or false? Well, it has to be true for all x's, okay? Well, how do we do that? Well, in this particular example, we just have to find a counterexample. Okay? If you have an all statement, to prove it wrong, just find a counterexample if you suspect it's false. So try 1. Suppose x is 1. If I plug 1 in here, I've got 2 times 1 plus 3, which equals 5 on the left side. If I put in 1 here, 1 plus 7 is 8. Is 5 greater than 8? No, it's not greater than 8. And so I put a slash through the greater than symbol because 5 is not greater than 8. So we have found one case where r of x is not true. So we could write there exists an x such that not r of x. And so that shows that for all x, r of x is not, that statement is a falsehood. That whole statement there is false. Okay? Another example, suppose there are 4 computers on a network labeled C1, C2, C3, and C4. If P of x is the propositional function computer X has a virus, then the statement for all x, P of x, can be written as, well, for all means all of them, so it has to be that computer C1 has a virus, and computer C2 has a virus, and computer C3 has a virus, and computer C4 has a virus. So if they ask you to write it as a conjunction using and, you're basically saying it's true for all of those computers, okay? Which is, kind of showing that you know what for all x, P of x is true means, okay? And then some more examples. Let P of x denote x squared is greater than or equal to x for all real numbers. What is the truth value of the statement, there exists an x such that P of x is not true, or not P of x? So we've got to examine that statement. There exists an x such as not P of x means there's some value of x where that inequality there, x squared greater than or equal to x, does not hold true. Okay, well, again, if you can find one where it doesn't hold true, then you've proven it wrong. You've proven it that there does exist a value of x such that P of x is false, which is what we're trying to prove here. So if you try x is 0.5, 0.5 squared is 0.25, and 0.25 is not greater than 0.5. 0.25 is less than 0.5, okay? It is not true that P of x is true. So anyway, the P of x squared greater than or equal to x is false in this case. So there does exist, all we have to find is 1. There does exist a value where P of x is false. So therefore the whole statement is true. Okay? I know this gets complicated, but try to stay with us here. All right, so the next example down here is talking about a restricted domain. So you might be, in your statement have a little restriction on it. So let me show what that's talking about. Right here is the restriction that x is less than 0. So for all x's less than 0, x squared is greater than 0. So this puts this restriction on it. So we're talking not just about all x's, but all x's that are less than 0. It could be written as an if-then statement also. for all x, if x is less than 0, then x squared is greater than 0. So this is a if-then statement, instead of using the restricted domain situation. Is this true or false, this proposition? Is it true or false? Well, actually, it is true, because whenever you take a number less than 0 and you square it, you get a number greater than 0. Because if it's less than 0, it's a negative, and when you square something, you're multiplying that by itself. So -5 times -5, for example, gives you a positive 25. -2 times -2, positive 4. So that's going to be true. Okay. All right. I think this is the last slide, but negating quantified expressions. To say it is not true that all people are good is equivalent to saying there exists at least one person that is not good. Okay. This is really using De Morgan's law. De Morgan's, or the original statement says it's false, or it is not true that all people are good. So this would be for all x, people are good. The opposite of that, so it's not true, is there exists at least one person that is not good. Likewise, to say it is not true that there exists a bad person is equivalent to say all people are not bad. These are called De Morgan's laws. All right, so here is in symbols. It is not true that there exists an x such that p of x is true. That means for all x, not p of x. Okay, and you can read it in when is the negation true? If for every x, p of x is false, and that's really what this is saying. But if you can find an x where p of x is true, then that statement would be false. It is not true that for all x, p of x is true. Well, that's equivalent to saying there at least is an x such that p of x is not true. Okay. All right. So, oops. So that's the end of the slide. So try the homework. The homework, of course, is the way that we can know if we're getting it. And so, it's not easy at first. It takes a little while. Now, you will be able to use your notes during a quiz. You won't necessarily be able to use the internet or things like that for exams, but for a quiz you can. And so we won't be on complete lockdown for that, but there's a practice quiz, and you can see if you're getting it doing that as well as in doing the homework. But send me your questions if you have them that I can help you with.